All right. So thank you for making it in today. Hopefully the room isn't too bad for you. Today, I'm happy to introduce Jason Moore. He's here visiting us from the University of California, Davis. Luckily, he made it in yesterday on his flight, despite all of our best attempts to keep him away with the weather. He did his master's and PhD at UC Davis, then did a postdoc at Cleveland State, all in engineering, and now he's been back at Davis as an assistant teaching professor for the last 4 years, and he's going to talk to us about one of his projects. So with that, I'll let Jason take it away.
Thank you. Thanks for having me here. I don't even know if I've been to Wisconsin. Also Minnesota. I'm dropped in there, so I have not been to this area. So I'm looking forward to see what you all have to offer. The snow is certainly one. So Devin came out to Davis a couple of years ago and talked to us about all of his work in open access and open science related to engineering. I'm sure that he tells you something about that too. But it's really good stuff, and he's doing good things on that front, and he's got a lot of exciting. There we go. A lot of exciting things. What is that? What do I do? A lot of exciting things up front. So, I don't know, do you guys have biomechanics here? Or how many people know what biomechanics is? Two? Okay. So, I did my PhD in a sports biomechanics lab and studied primarily things about bicycling. And I do some research projects in the broader sense of biomechanics and also sports biomechanics. So, this is a project that I've been working on with a set of my undergraduate students that has over a year now that has been looking at interesting things about rowing. But I wanted to tell you all about this. One, to introduce you to biomechanics a little bit. So biomechanics is the study of creatures, right, whether they're humans, animals, or other beings, and how to sort of treat them as a mechanical system. We can use a lot of the things that you learn in mechanical engineering to think about many of the aspects of how we function, how creatures function, and how they live and how they move. A lot of biomechanics that I work on is associated with human locomotion. So how do we get from A to B, and what are sort of mechanical principles that allow us to do that, allow us to control ourselves. My postdoc work was in power prostheses, so we worked to design different kinds of prosthetic devices that could mimic a human's behavior. There's a lot of the term biomimicry that we use a lot to try to influence machine design from the good things that come out of evolutionary design that we have gained. But one of the interesting applications here is sports. Okay, so anybody a rower here? No rowers. Okay, so we'll learn about rowing. I'm not a rower either, so I won't know all the details about rowing, but I teamed up with an interesting group of people. So what I'm going to tell you today, all the work is done by these students here. The guy in green is not a student, but the rest of them. So these are some of my undergraduates out of Davis, and all of them have graduated except one. Most of them have jobs, and so we're all in good shape. And at least one of them got a job directly related to the work that they did in the project, which is cool, but that's them. And I teamed with Paul, he's the guy in the center here that owns a company called Headline Technologies. He's the rower, and he's got sort of a smartphone-based app company that helps rowers train better. Does anybody use Strava for running or bicycling? So sort of the Strava for rowing, and I'll show you a little bit about that. And then also we have to team up with Seth is also in Paul's company, and he was a student of ours in our department about 5 years ago. I think he majored in mechanical and aerospace engineering, but he wanted to compete at the Rio 2016 Olympics as a rowing crew member. And as far as I know, he's going to try to compete at the upcoming Tokyo one once again. So I think he's training for that. So teaming up with some rowers there to do this work too. A little bit more about me. Like I said, most of the things I do are in biomechanics. You see some imagery here about the kinds of things that we study. I work on software projects that also relate to dynamics and biomechanics and how to create simulations and different kinds of analyses tools. And then one of my favorite topics is bicycling. My dissertation was called Human Control of the Bicycle. So I've thought a lot about bicycling. I teach system dynamics, vibration dynamics, I teach custom design, and we have a whole lot of fun. And this project actually started a custom design project. The guy that all came and wanted them to do a design project, and it sort of turned into a little bit different over the year. One thing that I think is unique about this project is that many mechanical engineers may not think that software development is the thing they want to do, or that's a big part of their project or their workflow. But this dynamics problem after growing, it turned into a development of algorithms and software to do so. So all the students became quite adept at doing software. So a little bit about rowing. There's competitive rowing. It's not like a huge sports market. It's pretty expensive. Like the boats are 20 grand a piece or more, and it's usually like a rich person's game, or a crew club in school you can be on without with the school sort of fronting a lot of that cost, or the rich alumni donors or something. But it is sort of a not hugely popular, but it is in the Olympics. There's huge events like the races on the Thames in England that are quite popular and televised and things like that. And it uses one of the two most efficient ways to extract energy and power from a human. The other one is cycling, but rowing is the next best. And to do that, we use our legs. So you may think that rowing is all about your arms, but it's really all about your legs. And this is a little video that gives some flavor of the kind of things that Paul with this company, Headline Technology, is sort of getting at. We're interested in providing different kinds of real-time analytics that a coach or the rower could eventually use to improve their training while they're going. So this is sort of a little demo. He has a rowboat. This is a double, and they are rowing or sweeping with only one oar, and it's called sculling if you do two oars. And the studies we do are in sculling, but this is sort of a sweeping. And he's got a number of data feeds here that are providing kinematics primarily, the different that are taken from accelerometers, rate gyroscopes, and he's trying to translate them into different interesting metrics that you would may want to look at and analyze for rowing. Okay, so that's sort of what rowing. This mounted a little GoPro camera on the front of the boat, a double scroll. And this sort of ties in, there's a big need in sports to have wearable sensors, these small sensors that can improve your training. We're going to see more and more of those who all maybe wearing the little watches that count the steps, but things are only going to get more elaborate as we move forward here. And analytics. So I'm going to focus mostly. We did our work on a single rowing skull. So you have one person in a single boat, and they're working both oars on the sides. So this is a skull. The boat you see is very tiny. They're used, the really nice ones are, I guess, pretty much all of them probably now you buy are carbon fiber. They're crafted in the same way that a fancy airplane would be. They're super light, and then there's usually some kind of aluminum, or if you get expensive, maybe you could get titanium or something. Oar lock system. So there's a pivot here at the oars. Most of the oars are carbon fiber too. They flex, and then they have specifically designed blades for that. And then also the person is on a sliding seat. Okay, so the sliding seat is critical so that you can utilize your legs as a primary mover. Okay, so that's what one of those looks like. This video shows Seth, the Olympic rower that worked with us. This is us just sort of riding by him, watching him on that single skull. I've got a diagram here that tries to break down the anatomy of the row stroke. Okay, so the first bit, we're going to start at the catch, and that is right now, as soon as the blades hit into the water, you have the catch, and then you drive by extending your legs back, and then pulling, holding, essentially extending your legs back and holding the oars in place and then moving the boat forward relative to the oars. And then you pull them out, and then this is called the recovery, which is the stage where they're out of the water and they're coming back, and you don't want those oars to hit the water. So you're trying to be a perfect oarsman here. The oars have to catch in a perfect way. You don't want them to go in at any incorrect angle. You want them to slide in sort of perfectly to reduce the amount of drag, and then have a maximum amount of thrust force that you can get with keeping those oars in the right orientation. And then when you pull them up, never touch the water while they're out, and have a nice no aero drag on the way back, so that you can maximize your rowing. So that is the basic anatomy. I'm going to use some of these terms to drive the recovery as we move forward and look some of the data. So we were interested in a few specific metrics. Okay, to win a race, you've got some distance along the water, and your goal is to go as fast as possible to get there. So we want to mainly boat speed, right? If my boat's faster, I'm going to win the race. So that's the big one. But each stroke that you make contributes to how fast your overall speed is going to go. And the other ways to break that down are stroke rate is a common metric that we talk about, and it's just how many times do you stroke per minute or some amount of time. Typically, it's strokes per minute. And we'll use some of those. Those are approximately for competitive rowing between 20 and 35, strokes per minute that you would see. And then this distance per stroke is a metric that we were particularly focused on, and that is the distance you travel in inertial space relative to the Earth during each time period of the stroke. And if I can increase that distance per stroke on every stroke, then I will go faster. Okay, so all these are tied together, but this last one is an interesting one to think about. And the way to maybe think about that is that if I'm doing a 2,000 meter race, you're probably going to take about 200 strokes in a normal competitive race. And it turns out that for the best racing that we see, that there's about a 0.5%-ish difference between the placement, right? Whether you get first, second, or third. Okay. So if you sort of break this down, what that amounts to is that in each stroke, if I could analyze and think about on a 5 centimeter level and be able to change things in my individual strokes such that I gain 5 centimeters, those would add up to maybe getting me another place. Okay. So we want to look at the stroke at a stroke level in an intimate view of that, so we can try to think about what am I doing wrong in those particular strokes so that I maximize my distance stroke. And every stroke is slightly different. And your goal is to have them all the same and all done in an optimal way. So how do we look at these strokes and sort of ensure that we can get this view down to a 5 centimeter accuracy of prediction on distance per stroke? So given those metrics, we want to get that data somehow off the boat. The typical thing on this boat is like you buy little impellers that you put on the bottom, and they can measure the water relative boat speed. It varies with current, which sometimes may matter, sometimes may not. And you can put your Kalman GPS on there. It's going to tell you a speed, right? Maybe that's a good measure. But we want to get a little bit better and more accurate than what those provide. Turns out those don't provide very accurate views, and I'll show you a little why in a second. We sort of went through 4 things here. We're going to collect a lot of data, right? It's going to be kinematic data. We're going to do something called sensor fusion. How many people have heard of the word sensor fusion? Okay, so sensor fusion is a fancy term basically for given lots of different measurements. How do I combine them in a way to maximize estimating some measurement that I want to know? And it turns out the more measurements that you take, and the more variety that you take, you maybe can increase your accuracy of things that you want. Okay, so we use this thing called sensor fusion to do that. We're going to compute these metrics that I just said, and then we want to estimate how good or bad we are at computing those metrics. We need some kind of ground truth to do that. So So let's look at this data collection. The first thing I want to remind you of is, you've probably seen this, you should have seen this in engineering class if you're seniors, is the idea of accuracy and precision. Okay? So I've got a graph over here that tries to visually show that this column is accurate and inaccurate, precise and imprecise. And you can see that if I have both accuracy and precision, the black big dot represents the truth, okay? And the little dots are the measurements around the truth. This one shows that all of my dots are grouped pretty close to the truth, and their mean, if I were to take them, would land right very close to the truth. So that has both accuracy and precision. The dots are still close, so they're precise. You know, every repeated measurement, they keep coming in, and they're at the same spot, but they're just off, right? So I have some bias and inaccuracy. And then we can look at the converse here, where the measurements are all over the place, but if I take the mean of these, they're still sort of surrounding that true value. And then this is the worst case scenario that you don't want. Okay, so this was a very important concept for us to carefully think about when we are trying to compute these metrics, trying to look at the data that we collect and make different decisions. So mathematically speaking, we work with a few definitions of this. The first one, for accuracy, we are using essentially something called central error. And that is, if I take the mean of some collection of those dots, and then I sum up the errors, this would be the truth and the measurement. If I, let's start with this one. If I have the mean, which is the truth, and I think I'm screwing up my labels. The S is the truth. The S is the truth here. If I have the mean of the measurements, I can then subtract, find the error of the difference between it and the truth, square those so I don't have to sort of deal with signs, and then I can sum x, y. If you had z, you could sum z in there, but this is just the how far away is the mean from the truth. Okay, so that's the exact mathematical thing we're going to use. The variance helps give a bit of the spread. So given the mean, and then I look at each individual measurement, how far away is the spread? So if I have them spread out far, this variance number is going to go up. So you've seen these in your basic stats class. And then one other important one is you may have heard of root mean square. Okay, and it turns out that almost anybody that works with sort of GPS data is going to use root mean square. It's actually the recommended standard to tell you whether something's accurate and precise. But it turns out that root mean square is really a summation of the central error, the accuracy, and the precision. Okay, so whenever we see these root mean square, you have to be careful because it lumps both of those up. Okay. So those are some of the statistical ideas that are important when I use the words accuracy and precision. That's what I'm talking about. So what kind of data? The data that we're working with is we put a smartphone on both. And a smartphone, does anybody know what the sensors are that are in a smartphone? That are interesting and useful? What are dynamics? There's accelerometer there. Yeah. What else? How's Google Maps work? GPS. I think I heard a whisper there. Anybody know what there's two more sensors that help with dynamics. There's an angular rate gyro, so that tells you the angular rate. And then there's even a magnetometer in there that can help you with heading orientation relative to the magnetic field. So those are all in there. So we're going to use a smartphone and try to get these estimates. And I'm going to show you first sort of how that smartphone is. These are the measurements, the primary ones. I'm not going to talk about the magnetometer at all. It's sort of an even worse measurement. But the acceleration and gyro measurements actually are good in of themselves. Okay, but if you want to turn that into orientation or position, that's difficult because we have to integrate an acceleration twice to get a position, integrate a rate, angular rate once to get a angle or a velocity. Okay, so we got those, and then we also get this GPS view of the location of the object. And then one note here, right? This is you get 3D information here, so it's got all that. Full angular velocity vector, full linear acceleration. All right, so global, you also get the GPS. So a little bit about GPS is that it's not that accurate, and it doesn't really update that fast in a smartphone. So we get these signals from these networks of satellites that we can sort of ping, and then the triangulation that you mentioned is used to let us calculate an absolute position on the Earth's surface, right? It turns out, though, that in the smartphones, you only and in most GPS things, unless you're paying for military grade GPS, you're going to get very low update rates. Okay, so we get about a third of a hertz. Okay, so only once every 3 seconds. And the next thing I'll say is about this is that the error in your GPS is pretty bad. And you may have seen this in your smartphone. Maybe you're standing at the clock tower there and it's showing you 10 meters off or something. So you probably have seen that and experienced that. But it turns out the absolute accuracy can be quite bad. And I'll show you a little picture of that. The relative accuracy between subsequent measurements is not too bad. So if I take a GPS signal here and then move 1 meter, it's going to tell me pretty good that I moved a meter, but I might be 10 meters off the actual place that I'm supposed to be. Okay, so that's okay. And then the precision, which is related to that, is pretty decent, but it's still not down to any 5 centimeter levels that we need to. So we're seeing 1 meter on these kind of things, just from point to point that I know. And then I also wrote that the smartphone gives you speed, right? It'll tell you if you're driving in your car, it'll tell you your speed that you're going. And it's not a simple differentiation of this position data. The Android and or Google and Apple, they have some proprietary ways to try to give you better estimates of speed. So you do get a sort of independent measure of speed, but it's a little better than if you just did DXDT on that. So here's an interesting picture, I think, that shows that a bit. This picture shows these purple dots. It might be a little hard to see. That is a true location that they mapped out using surveying techniques, right? So that we can get a true location. And then they took us different smartphones, Android, the tablets, on different kinds of devices, and they laid it at that point and just left it there, and then let it measure for some amount of minutes. And you can see, like, this is a car, right? These little dots, it's a parking lot. And for example, that group of things is supposed to be on that one point. You can sort of get a sense of how awful the positioning data is. So if we want to get 5 centimeter accuracy, I don't know how you're going to do that with this kind of mess. So we see there's a lot of error in there. We just do not have a super accurate local positioning at the consumer grade level. In the military, they can drop a bomb on someone's nose, I guess. But that is not something that's readily accessible to us. So that's just gives you a sense of the GPS and maybe how poor that is. The other thing, for us to get distance and speed traveled, we're going to primarily look at the acceleration that the smartphone provides. Okay? And what I have here is a rower that's traveling this direction, and we mounted a smartphone on here. Turns out, though, that you mount it slightly off on the boat, but relative to Earth, really relative to the gravity vector, that smartphone has some arbitrary orientation. And then the boat also pitches about plus or minus 1 degree as you're rowing, a typical rowing scull. Okay? So this theta is going to vary, which is the smartphone's orientation. Now that is a problem for 2 reasons. One, the axes of that accelerometer in the smartphone are stuck to the smartphone. So the axes are moving. We don't have like some fixed inertial system. We need to know, where are they pointing? If I want to know acceleration along the boat and my sensor is moving like this all the time, how do we do that? Well, maybe I need to know theta. The other thing is that an accelerometer is not really an acceleration measurement device. It is a force measuring device. There's literally a tiny little beam inside the accelerometer that's made of, at micro or nano scale, and it bends. If I move an accelerometer, the beam will flex backwards, and it's really measuring force. So it turns out that if I just hold it here, the beam's bending down because gravity's pulling it down. So you have to subtract subtract out this gravity vector too. Right? So there's this component of acceleration that is varying, and it gets multiplied by this large g vector, which is 9.8 meters per second, is quite much larger than the acceleration of about, I'm trying to think our max acceleration is certainly less, I think it's about a tenth of it maybe. So we've got to get rid of this. And what I've got here is, this is the acceleration of the boat that I want, right? That's the vector I want. This is the thing that the smartphone outputs, okay? And they're related to each other by this angle theta. So this is the vector equation, that the acceleration of the smartphone, I have to subtract out the gravity component from the smartphone acceleration vector, the one that it reports. And then if you take that vector equation and look at, boil it down a little bit, if I want to know the longitudinal acceleration of the boat, it's approximately the y value of the accelerometer, even though it's moving around, but minus g times theta for small angles. Okay. So that's the basic thing. I've got to somehow subtract it out, but I don't know theta, because the smartphone doesn't have a direct theta measurement. In fact, measuring theta is a tricky thing. It tries to measure it, but it's not such a great value. Any questions on that? You guys ask me questions too. Right. So we got some funky things to do with that accelerometer to try to get the actual linear acceleration along the path. This is what the acceleration data looks like that you do take off. So this is sort of the raw value of that axis that's going up and down the pitch for a rower. This one is two rowers. One we call the club level, and one the elite, and that was the Olympic guy, and that was the guy that rows every weekend. So not that I'm not showing, they're not that different in graphs, but they're both there. We plot here percent stroke, and then this collection of sort of blurry orange lines are all the strokes in some trial. So I look at from catch, when the oars go into the water, drive, and then back to catch, that's 100%. Okay, so we go catch to catch is your 100%. So this is also catch when the oars go in the water. And then this shows the cyclic behavior of that, of the acceleration that you see in the drive, right? We start to accelerate, and then there's no acceleration, and then you start to slow down to the drag of the water, and you don't have any propulsion. So these measurements are actually quite nice. You get them at about 100 hertz by default on the smartphone, and you can see that they're pretty repeatable, nice quality looking data. So you do get a really good acceleration value off these phones, and that's what gives you a sense of what they look like. Now, if we want velocity and position, we've got to integrate once and then integrate again. And what I have here, I wanted to give you some sense of the problems with that. This was a little simulation of rowing that had some basic thrust. The longitudinal position of the boat, so that's just x value increasing as I apply that thrust. This is the velocity, the derivative of that. And so you can see every time I thrust, it speeds up, and then the drag of the boat slows down, speeds up, slows down. And then this last is then the acceleration, which is the derivative of that. So this is x dx d squared, x dt squared. Right? So there's three derivatives there. We're measuring this one, and we want to go backwards by integrating. Well, if you do that and you integrate, there's always a problem with noise in this sensor. So there's two types of noise, both an accuracy and a precision noise on a given accelerometer or a rate gyro. And with that, I'm going to draw this a little bit. What that looks like, if I look at time, some accelerometer value that I took off there, if I just hold it, lay it on the table, and it does nothing, and I take one of those readings, it's going to jiggle around some value. Okay. And typically, there's sort of a constant bias. So if I took a mean of that, there's some bias there. And if it jiggles, you can also look at the spread. So if I do thought of some kind of standard deviation of that spread, this would be the accuracy and precision of that signal. So if I want to integrate a signal like this, this bias, which isn't always constant, but for this example, we'll sort of assume it's constant. What happens when I integrate a constant? In the wrong direction. All right, I get an x, I integrate again, I get an x squared. So that x squared term is lumped up in here. And when I integrate, I've got to extract that, right? And I don't know what that, if I don't know the bias, I wouldn't be able to subtract away this part of the integral that cause me trouble, right? And this is sort of what happens when I do that. This is the actual velocity, the blue, and then if I take that accelerometer signal you see right there and I integrate it, just numerically integrate it, then it drifts off, right? And that is due to this bias being present. Okay, if I know what the bias is, that's fine. I can figure out how to subtract it out. But in general, you don't know what the bias of any given sensor is. Sometimes you can characterize it, but they usually fluctuate and it's just a mess and you just don't know how to deal with that. So this is called drift, right? Anytime you have to integrate a signal and it has a bias, it's going to drift away from what the reality is. You can't account for that. So we got to deal with that. Those are the two primary sensors. We're going to look at the GPS data, which gives us position. It also is going to give us a speed that the smartphone calculates. And then I've got this accelerometer that's a really nice signal. And if I integrate it, it would give me a beautiful position, maybe even down to 5 centimeter accuracy position, but it's got bias. And I don't know how to solve that. The next thing, okay, so we got these sensors, and I want to take those measurements. I want to get these three metrics, both speed, stroke rate, and distance per stroke, right? To do so, how do I know that I'm getting the right answer? Just like the people with the smartphones that went out with a surveying technique and found the truth and then put the smartphone there, you need some ground truth data. So what we did is we bought a better sensor that could give us more accurate measures, and that is called a differential GPS. It turns out that a lot of the error, a lot of the bias in your differential GPS, the reason it's off like 10 meters when you're standing there is due to a number of things, but one is like atmospheric effects. That given set of GPS receivers that you're seeing from your smartphone, there are going to be effects that are the same for every smartphone. And in fact, if you took everybody's smartphone and laid them here, they would all, and they're looking at the same satellites, they'd all have the same error, mostly. Right? They'd all be 10 meters off. And that's because basically the communication from you to that particular satellite has a built-in bias due to the atmosphere and how that signal is coming across and the rate and what clouds that is. Well, if you take two GPS receivers, you can get relative position between them and ignore that bias. Okay, so if I have more than one GPS signal, I can. They're both off 10 meters, right? But I already told you the precision of the GPS was a little bit better. So then I can just subtract away the 10 meters from both, and if I move one GPS relative to the other, then I've got very accurate measurements relative to the other GPS. So the way the different GPS works, you have one GPS receiver, you hold it still, and you move another one around. And then there's some interesting math that will let you subtract away the bias. Then you've got a very accurate measurement. It turns out this thing, we have now been doing up to over a kilometer away, we've been getting 1 centimeter accuracy measurements. So if I stand here with my 1 unit, and we've been doing a ski work now. I can show you a slide of that at the end if you want to see, but my student, Bryn, she puts a differential GPS hat on her helmet, and we ski up into the mountains of Tahoe, a kilometer away, and I can know her position in XYZ in 1 centimeter, which is phenomenal. Okay, so we use that. This is the roving one, and then we have another one that's on the shore that's fixed. And what that lets us get, the sample rate isn't as good as the accelerometer, but it's up to 10 hertz. But then we get that 1 centimeter accuracy, and then and this is the precision, right? So it's super good. So this is what we consider in our ground truth. So if I take this sensor and then I put the phone on the boat too, and they're moving on the same rigid body, then I can say, I can compare the phone, what the phone tells me we're doing, to what the differential GPS is, and use that in ground truth. So that's what we did there. So this is our basic setup. Was set on the boat, the phone, the GPS, and then the GoPro. This is, I think this is him going at one of his max stroke rates, around 30 strokes per minute. And so this is one of the best rovers in the world. If you want to, see, he's it's been a few years since the 2016 Olympics when he was prime, but he's still very good. And if you look at each of his strokes, he's like never touches the water when it's out of the recovery. They're perfect balance. Just sitting on this boat is that you can't balance on it, right? If you try to sit there and hold the oars out, you'll go over. Every one of us will. Almost even professionals will. He can sit there though and just balance. That's how good he is at keeping the perfect balance. You see a little bit of roll, but in competitive rowing, you do see it's about 1 degree in all of the axes of rotation during rowing. But that is one of his higher speed runs there. There he is doing balancing like that, which is nuts. I'm deep into my time here. 10 minutes left. This is the first time I gave this talk. Few minutes? Yeah. You told me 11:05 on that talk?
10 to 15.
After? Okay. All right, we'll see. I'll see that. Here's an example of the differential GPS data, the base station, right? We get very nice results. You see, this is speed now that it is. That we calculate through just a basic central differencing on that, do a numerical derivative. We see a little spread there. It's not as tight and as nice and repeatable as the accelerometer, but it still has that positional accuracy. This is way better than the smartphone by an order of magnitude. Okay, so the sensor fusion, I think I will, since I am taking a little time, we'll see where we go here, but I've got some data and I want to do some sensor fusion. What that means is, okay, I got those measures. How do I optimally get the three things I want? The boat speed, the distance per stroke, and the stroke rate. Okay. So this is the basic idea. We actually we're able to develop a real-time way to convert these measures into the accurate thing that we want. And the top part is the real-time estimate of what we want given the smartphone, and this bottom portion is how we took the differential GPS data to make the validation data, and then we compare them to figure out the error. All right, so I start with the smartphone position and accelerometer. You got to do some data cleaning. This is just that, but then I get longitudinal acceleration and distance along the path. This is the GPS, and that's the accelerometer. I fuse them with a filter, and then I get a better estimate of, I get an estimate of distance along the path and speed, okay, which then I can use to compute distance per stroke and stroke rate. That was a ninja catch. We have to determine the start and stop of each stroke from that data, from both the differential GPS, and do it at the same time, and then we can basically calculate how bad am I estimating. So we do two things. We tried two different methods. One of them is called a complementary filter. And the gist of this is that when you integrate that accelerometer the drift that I showed is a low frequency component, right? It is not something that's jumping around. And if you turn this into the frequency domain and I subtract away low frequency, it basically deletes that drift. So you can eliminate drift by using a basic frequency-based filter. And then the typical way you do this is you use a low and a high pass filter. The low pass filter, the high pass filter is when whatever signal you have drift on, and the low pass is whatever you have a complementary signal that we can take just the the low portion of those. And in our case, we low pass filter the speed and high pass filter the integrated acceleration. Sum those together in the frequency domain, we're able to get a better estimate of speed. And then we do it one more time to get the distance. Right? So I'll give you, you have seen a segue before to know what a segue is. So this is a little simulation. This is what I do in my system dynamics class, one of the projects they do. You got to make a segue balance. And it turns out that if you put an accelerometer and a rate gyro in there, it doesn't measure angle, but that's what you want, right? You want the angle to stay up. And that's what we really like to care about. The classic way to figure that out is take the accelerometer and the rate gyro, integrate it, take only the high portion of it, so the bias is gone. You can sum those together and it'll tell you the angle. And then you can use that in your controller to make your segue. So that's a typical way. If you look at any of the instructables and self-balancing little robots and stuff and want to make one of those, they're going to have that complementary filter to do the same idea. So that's just an analogy. And here's a picture of, this is that graph I showed you earlier with the drift. But if I low pass and high pass, this here is the same signal as that, but I've used the frequency, I've taken away the low frequency content, and it leaves me with just what I want. And then I sum those, bam, I got the complementary filter velocity now matches the actual. So using that technique, you can get rid of the drift. So that's one way we get it. The other way is called a Kalman filter. I think what I'll do, I was going to try to use 2 slides and explain to you the Kalman filter with nasty linear algebra problems and statistics. But we can do that after if you want to talk about that. Okay? But the gist is that you have a measurement and a model, right? And we all know, we work on lots of models in our dynamics class. And in our case, it's only kinematics that we care about. We know that if I am standing here, or if I'm here in an instant in time and I have a velocity, well, I'm very likely to be some distance ahead of me at time delta t in front in the future. So that's a model, right? If I know the velocity and I know that dx dt equals v, then we can predict where you're going to be in the future. So I use that model, but I can also have the GPS is giving me some speed value, which is bad. But if I take both of those and I have an idea about how uncertain each one are, you can use that uncertainty information and use those 2 signals. Based on the uncertainty information, you'll get a better measurement, a better prediction of the speed. Okay, so this basically shows that the model would predict this distribution of the location. The measurement tells me that I'm here. And then if I take these 2 distributions, I can generate a distribution that might be a better estimate. That's like the high-level concept of what a Kalman filter is. I will spare you the math if you want to talk about that. But those are the basic kinematic equations. If you're taking controls, you've probably seen the state space form. We put them in that form, but it's for a set of difference equations. And then there's this process that lets you merge based on the uncertainty. Okay. And I will, that's my 1-slide Kalman filter, which we have a whole graduate class to get this whole thing. But I'm going to show the first equation, and that's it. But the gist is that this is your measurement, right? So say I measured speed, right? This is what my model just predicted speed should be. So this is the error in speed, right? The model says the speed is something, my measurement says it's something. So I take the error and I multiply it by some matrix, okay? And I add it to the prediction. Well, I'm gonna screw this up by not having enough information, but this is the predicted state, right? So that's both position and velocity in our case. And if I look at the measurement error and I multiply it by these values, I can add or subtract to my estimate of the current state to get a better estimate of what the position and velocity is. Now, picking what this thing is, that's the tricky part, right? You have, there's two tricky parts. One, setting up the model, but getting L, and the math below basically shows you how you get L, and it comes from the uncertainty information. Like if my sensors are really bad and my model's really good, then I can use the model more, and L is going to weight in favor of the model, right? This number is going to be small, but if the measurements are very accurate, then this one that'll be a big number. Right? So that's the gist of the Kalman filter. So let's look at the results in the last video. We set up these two filters. We take the streaming data from the accelerometers and the GPS, and then we see how well we can estimate those three things that I wanted at the beginning. I'll skip this to show the detail about the Kalman filter. This shows distance. This is a single trial, right? And I have from, this happens to be 30 seconds to 60 seconds. This is the same set of data. This is just a different view. If you start at the top one, the black line, that's my gold standard. That's the differential GPS. It tells me how, every second I've traveled some amount of distance on the boat. And that just shows it increasing during the run. Okay? But the black line is the truth in our case. The smartphone only updates these blue dots. Okay. And you can see that the blue dots don't fall on the black line. Right? So it has some inherent error there. But it does sort of track in the same slope, which is good. Right? That's sort of the relative strength of the GPS signal. And then we have the results of these two filters. The orange one is the complementary filter, and that almost nails it, right? So it gives us the truth, even though I've got the same bad measurements as a smartphone. And then the and then the Kalman filter is the KF, the green. It fills in the gaps between the dots, but it sort of hangs off, and it's actually susceptible to the same bias because it tries to go. The complementary filter actually doesn't consider the measurements too much, but the Kalman filter does, and it does it a little too much. And we weren't able to get the tuning better than that. Then this is just, if I subtract the green, blue, and orange from the black line, and then plot that, it gives you the error instead. So we see that the complementary filter is very low error, low spread. The dots here are really the main thing to look at. They are off, the spread may be a little low, and then the spread's low on the Kalman filter. Precision, but the accuracy has an issue. If I do that for all trials, you can make these little distribution plots that show that distance. And here, I'm calculating the root mean square, which you remember was a combination of the accuracy and the precision. Right, so it sort of lumps it all together. If I have a very low root mean square, I either have very good accuracy and precision, or potentially one of the other. Right, it could be that case too. So this is the Olympian guy and the club guy. The smartphone gives distance estimates on average 4 meters of root mean square error. Right? The complementary filter for both of them gets a little better, but the median here is about 2 meters, but it still has a pretty large spread. The Kalman filter is worse for the elite. And then finally, the Kalman filter was better for the club. And that has to do some with, we try to tune these to be general for lots of rowers and it's hard to get them right first time. But we do see some improvement in distance estimate for 3 of these. So we get some improvement, but I'm not down to 5 centimeter accuracy. Okay, on overall distance. This is sort of like this is sort of the summation of like how bad are you off at every single time step as an aggregate. So the speed, I think, is a more remarkable result here. The black, once again, is that's our gold standard, what we want our predictions to be. You can see that the smartphone, it just gives you these updates at every little rigid, for every step that you see there. And you can't really get a good estimate of speed. And it turns out that strokes are about the same order of frequency as the smartphone update. So a smartphone is skipping strokes sometimes. Like you can't get any intra-stroke view. You have no idea. But you can see now that because we've integrated this accelerometer, that both of these now show you what happens between every smartphone update in a very detailed way. And with only a smartphone, I can then get starting to get very accurate views of the speed. And that's between every stroke. And it's down to 100 hertz. In fact, 100 samples per 100 updates per second, we're knowing what the speed is in a pretty accurate way. A similar graph shows the improvements there. All right, so the smartphones mean they're between 0.5 and 0.6 meters per second. And then we can at least double that in accuracy. And I think this is conservative too. If you look at the prior graphs, it gives you a lot of intra-stroke information. But, this one doesn't as much show. So the last thing is once you get the distance, you can slice it out at each stroke, and then we can look at that distance per stroke measure. And that's what we wanted to get down to this 5 centimeter value. The smartphone is on the order of median 1.7 to 2.6 meters in error. So if I want to know any given distance per stroke, it's awful, right? I just never got. It's going to tell me within 2 meters what your distance per given stroke is. We did get improvements here. You can see that now we're down to something on the order of half a meter, 50 centimeters. That's still 10 times what we wanted. Right? So we were not able to get to that, our original goal of that 5 centimeters with the algorithms and the tuning and the methods we did. So we're a little disappointed. We thought that we would be able to get that better, but it's a fundamental limitation on essentially the uncertainty of that GPS data. It's just so awful. It's hard to make an algorithm be magic enough to get it a lot better. But we do get quite a lot of gains here. So we get this better intra-stroke view and improvement. So we're making a stride forward, and I think more work. We've got some ideas of how to push it down more. Maybe we get it. So maybe not the grand conclusion we wanted, but we wanted 5, we only got 50. But we did see improvement in almost all of the things, from 40% to 70%, 80% improvements from the smartphone. So there's no reason not to use this, right? I might as well put it on my boat, have it running live on the smartphone app, and it can give me all these metrics, even in real time, way better than the given smartphone, or just looking at the base smartphone data. Okay, so it's an improvement to the Strava for rolling the app. Both of the filters are comparable. I didn't get to talk about this much, but the Kalman is adaptive a little better. It turns out that it does, given different rowers, different boats, it will figure out the bias in real time, and you don't have to rely. Well, that's a good thing. Just you can ask some questions about that if you want, but it does take 30 seconds to figure out that bias, and that is a significant portion of the row. So that's not that great, but This, though, I think is special. Now you can look at your speed variation for every stroke at 100 samples. Which you couldn't before with a smartphone data. Any GPS thing is not going to give you that. The only thing that could give you that would be those impellers that we put in the boat, but they are susceptible to the water flow, and there's no way to subtract that out. And then the final big conclusion is that if you carefully think about your application and what your smartphone's set to, you maybe can write a filter and create some algorithms that will improve the measurement quality of what you particularly interested in. And there's a lot of things you can use that for, right? There's any kind of motion, right? They use them in cars, they use them in all these sports things, they use them in any vehicle you can imagine, farm equipment, right? Buying the roads, right? All the stuff. So this thing can be applied to anything like that to give you a gain in accuracy, right? So if I'm plowing my rows and I want to improve the precision and get this better rows, well, do that correctly. So it's there's all kinds of applications. And if you all watch sports, you've seen over the last decade of all the kinds of interesting features that even that are put in to give data analytics about. There's now sensors in the helmets of football players. You can track all the balls and implements that are used in different sports, and you get kinematic useful information. And you're going to find these little sensors in every sports implement that exists before we know it, and you'll be able to pull this data on your phone for your personal or whatever use. So that's sort of the kind of things that we're looking to do there. So if you want to know more, this is our team again, with me in this case. And I put my preprint of my paper on the engineering archive that Devin is the lead on. So you can go and read that. It's getting reviewed right now for a journal publication, which is pretty amazing. Like most, undergraduates getting a journal pub, pretty remarkable. And that was super impressive of them. They also, all of their software, we put it on GitLab. So if you want to run the code and look at the notebooks and things that we use to do this, it's all there. Check it out. And if you want to see what my lab does or anything else about me, there's a bunch of content. So I hit the 15 mark. Without doing my 2-slide common filter detail, I'm sure you all have to have missed.
All right.
Thank you for your attention.
Thank you.